Alright guys, welcome back. Today we're going to talk about calorimetry. It's not a long podcast and there's not a lot of new material here, but there is a lot of math, so make sure you got your calculator with you. Get ready to take some notes. Alright, calorimetry is all about the accurate and precise measurement of heat flow into or out of a system for chemical or physical processes. You should write that down as a definition of calorimetry. Remember the Cheeto? We couldn't measure the energy of the Cheeto itself, so we had to do it indirectly by burning the Cheeto. Well, that worked pretty well, and we went and we heated up a can of water with the Cheeto. The problem is, I know we lost some energy somewhere. So part of what calorimetry is it's trying to be accurate and it's trying to be precise. So it has a way to capture all of that information. Now, we usually use water for this process, like we had water in the can above the Cheeto. And why do we use water? Well, we use water because we know so much about it, and we know that it has a specific heat of 4.18 joules per gram degree centigrade for water. And so it's real easy to use, and it captures the heat. So that's why we use water. Now, a calorimeter is an insulated device that measures the absorption or release of heat. So this one that we see on the left over here, this is really a fancy schmancy calorimeter. It has its thermometer built in. It has a stirrer so that you can stir what's going on with the water that's on the inside to make sure you get a consistent temperature. We have something that's sealed over here that goes and has the sample in it so that you can do whatever you're going to do with the sample. And so let's say we were going to burn a Cheeto. We could do it in here in this thing that's inside the calorimeter, and it's very, very, very precise. Well, we don't spend that much money in a school, so what we do is we use this thing over here, which is our basic cheap calorimeter, and all it is it's two styrofoam cups that one nested inside the other, and we got our thermometer here, and typically the reaction that we're doing is just something that goes in water. So we'll add something to water, may have a chemical reaction, and the chemical reaction takes place in the water, and the temperature of the water changes. So that's what it's all about. So this is what we use over here for a calorimeter. So when you do your labs in class, you're going to be using a calorimeter that looks a lot like that. All right, we need to remember what delta H is. We've talked about enthalpy before, and that's the change of heat in the sample. So we're talking about the heat content of the sample, and we use two equations that we're going to use for calorimetry experiments. And one of them is Q equals mc delta T. And if you remember this equation, our mass is in grams, and our temperature is in degrees Celsius, and C, our specific heat, is in joules per gram degrees Celsius. So when we get rid of grams and degrees Celsius, we are left with joules. So our answer here is joules. And when you look at a delta H for a reaction, typically your delta H for the reaction is in kilojoules. Now that's kilojoules for the entire reaction, all right, which is often for a mole of the stuff that you're using. For example, let's say that I had a reaction between, that was good, HCl and NaOH, right, and that is a neutralization reaction, and we get water, which is HOH, plus we get NaCl, right, and we're going to get some heat, actually, because this is exothermic, right. And so we would say that our kilojoules, our delta H, is going to be some negative number, and it's going to be in kilojoules. And it's kilojoules for this entire reaction, which happens to be for 1 mole of hydrochloric acid or 1 mole of sodium hydroxide. Right? So we're going to use those two equations, but what you really need to notice is this one appears in joules, this one down here is in kilojoules. Right? So we're going to have to make sure we make that conversion when we actually do some math on our problems. Okay, so here's the first of two problems we're going to do. We have 2.25 grams of ammonium chloride, and we dissolve it in 100 grams of water. The temperature of the water drops by 10.3 degrees Celsius. So what's the delta H of our reaction? Well, the first thing we have to do when we do this reaction is we have to come up with a balanced chemical equation. So let's see, we have ammonium chloride, which is NH4, Cl, and it's dissolving in 100 grams of water, and so that means it's becoming NH4, which is a positive ion, that's your cation, plus Cl, which is a negative anion. Those are both aqueous. They're both dissolved in water. Right? And the temperature drops. So this is absorbing energy over here. So some number of kilojoules of energy is being absorbed. And that's what we're trying to figure out. So this is going to be an endothermic reaction, which means it's absorbing energy. So we're going to have a delta H that is positive. We don't know what that number is, but it is going to be positive. All right. So let's go ahead and do some math and see what we can do. What we can do. Well, remember, we're trying to figure out stuff about ammonium chloride. The problem is we can't measure that directly. We have to measure it indirectly by what happens to water. So if I look here, I've got 100 grams of water, and the temperature of the water is dropping 10.3 degrees Celsius. So I can use my equation that says Q equals mc delta T. And this is specifically for water. Right? So what I have is I have a mass of 100 grams of water. That's 100 milliliters of water. And I'm multiplying by, I really should do that. Let's do this. 100 grams of water. And my specific heat is 4.18 joules per gram degree centigrade. And again, remember, that's all water. Times the temperature is changing by 10.3 degrees Celsius. So my degrees Celsius is going to cancel, my grams are going to cancel, right? So when I do the math, I come up with 4,305, because that's 418 times 10, so 4,305.4 joules, which, by the way, also happens to be 4.3054 kilojoules. Either one of those is fine. But I know I'm going to be using kilojoules, so I did my conversion simply dividing by 1,000. You need to know how to do that. All right. So what's the delta H of this equation? What's our delta H? Well, our delta H is kilojoules per reaction. All right. So our kilojoules is 4.30, let's see, 4.3054 kilojoules, and we have to do that per moles of ammonium chloride because it's 1 mole of ammonium chloride, so we have to do it per mole of ammonium chloride. Okay. So we got this much energy coming out of 2.25 grams of ammonium chloride. The question is, how many moles is 2.25 grams of ammonium chloride? So if I start with 2.25 grams of ammonium chloride, that's NH4Cl, and I had to convert between grams of NH4Cl to moles of NH4Cl, good gosh. Well, I had to figure out how much NH4Cl weighs. Well, nitrogen is 14.007. Hydrogen is 1.0079, but I'm multiplying by 4, and my chlorine is 35.453. So I add all of those together, right, and what I come up with is 53 grams, 0.492. So you can do the math there, but I just figured I'd save you the time. So it's 53.492 grams of ammonium chloride in 1 mole. So if I do that math, I come up with 0.0421 moles of ammonium chloride. Well, guess where that goes? That goes right up there. So it's 0.0421 moles of ammonium chloride. So let's think about what we did. We got a certain amount of energy coming out of this many grams. So we got a certain number of kilojoules coming out of the reaction that we had. So that's kilojoules per mole, and we have kilojoules per mole, but we only have a little bit of a mole that we used. So that all makes sense. And when I do that math, I come up with, if I actually divide that out, I come up with 102 kilojoules. So my delta H is going to be positive 102 kilojoules for this reaction. All right, let's go ahead and try another one. Iron 3 oxide reacts with aluminum. The delta H of the reaction is negative 851.5 kilojoules. Is it endothermic or exothermic? Well, what do you think? Pause the video, come up with an answer. All right, well, when the delta H is negative, then that tells you that it is exothermic, it's generating heat. Now, I know that we're about to do a problem, but to do the problem we need to have a balanced chemical reaction. So let's go and come up with a balanced chemical reaction for iron oxide reacting with aluminum. So pause the video, see if you can do it on your own. All right, hopefully you did that. We have iron, we have oxide. The iron is +3. This is -2, so when I cross them, I end up getting 2 irons and 3 oxygens, and I'm adding to this aluminum, and I am producing aluminum oxide. Right, that's going to be AlO, and the aluminum is +3, the oxygen's -2, so it's Al2O3. Plus we come up with some iron. All right, now I have to balance my chemical equation, and I have 2 aluminums and I have 2 irons. And my delta H for this equation is going to be negative 851.5 kilojoules. All right, so that's for the whole equation. So that means if I take 1 mole of this, 2 moles of aluminum, I'll produce 1 mole of aluminum oxide and 2 moles of iron. All right, so it's very important that we understand what those ratios are. All right, so now our chemicals are dropped into 1 liter of water. So we're dropping these chemicals into 1 liter of water. All right, so we have some iron oxide, and we have some aluminum, and we're dropping it into water, and we're getting aluminum oxide plus iron. And we've already said that our delta H is negative 851.5, so I'm also getting out of this my delta H is negative 851.5. Did I write that down right? 851.5, yep, kilojoules. Kilojoules. Okay, so if we have 23.5 grams of iron produced and the temperature starts at 20, what's the final temperature? Well, again, we have 2 things here. We can tell that our delta H is equal to kilojoules per reaction. All right, now since we're talking about iron, that's 2 moles of iron that we're talking about. Right? So let's actually go and convert iron into energy and see how much energy this would have created. Well, let's see. We can start with the information that we're given. 23.5 grams of iron, and we have to convert from grams of iron to moles of iron. Right? We know how to do that. 1 mole of iron, we look up on the periodic table, and it tells us it's 55.85 grams. Well, so far that's pretty easy. Now here comes the slightly tricky part. All right, the tricky part says I have to convert from moles of Fe to kilojoules. So the question is, what's my ratio here? Well, look up here at the top, and you'll notice we have 2 moles of Fe generating negative, well, let's not worry about the negatives. We haven't worried about those before. 851.5 kilojoules. So you'll notice the key thing here is that it's 2 moles of iron. So we have to make sure we put the 2 in there, or else we're going to get the wrong number. Okay, so we sit here and we divide all that out, multiply that all out. We get 179 kilojoules of energy that were released, that were created from 23.5 grams of iron. So those are our kilojoules. Now what? Well, we know that we have 1 liter of water. 1 liter of water is 1,000 milliliters, or 1,000 grams. All right, so we know that Q is equal to mc delta T. Now remember, what units is Q in? Q is not in kilojoules, it's in joules. So if I take the kilojoules and I convert to joules, that's 179,000 joules, and that's Q. Now how much water do we have? Well, we have 1,000 milliliters, which is 1,000 grams, so that's 1,000. And C is 4.18, and that's joules per gram degree centigrade. And what we're trying to figure out is our delta T. That's what we don't know, right? And that's going to be in degrees Celsius. So how do we do this? Well, we have Q, which is joules, and if we divide by these two things, we're going to be left with degrees Celsius, right? So Q divided by M, let's write that over here. Q divided by MC equals delta T. So that is Q, which is 179,000, and that's in joules, divided by 1,000 grams, divided by 4.18 joules per gram degree centigrade. Right, and we'll notice that my grams cancel here, my joules cancel there. I'm left with 1 over degrees Celsius, which is degrees Celsius. So my answer here is going to be, when I actually do the math, I come up with 42.9 degrees Celsius. There's my answer. Well, no, it's not. Okay, that is the temperature change. This is delta T. That's how much the temperature changed. But the temperature started at 20 degrees Celsius. Now, because our delta H is negative, that tells us this is an exothermic reaction, so it's generating heat, so our temperature is going up. So we have to add this to 20 degrees Celsius to start, which then gives us a final answer of 62.9 degrees Celsius is our final temperature. Or, okay, so you can round if necessary, but there's your 62.9. Okay, that's the answer to that one. That's it. Now you've got some problems to do in your worksheet. Please make sure you do your worksheet. It's very important because these are the problems, these are like the problems you're going to see on a test. All right? Have a good day. See you in class. If you have questions, we'll help you out. Take care. Bye-bye.